In this video, we are going to talk about limit theorems. We'll start with just reviewing the definition of what it is to be convergent, for a sequence to be convergent. We'll look at the algebraic operations and how they affect limits, as well as a theorem about when you have two series that you want to compare, and you know that one is convergent. And then last, we'll talk about infinite limits. As I mentioned, we're going to start with a review of the definition of convergence. So a sequence is said to converge to a real number s, provided that for every epsilon greater than 0, there exists a natural number capital N, such that for all natural numbers little n that are greater than or equal to capital N, this implies the distance between Sn and s is less than epsilon. Our first limit theorem involves algebraic operations. So suppose you have two series, Sn and Tn, and they're both convergent sequence with the limit of Sn equal to s and the limit of Tn is equal to t. Then when you add these two, so the limit of Sn plus Tn, so you add term by term, is equal to s plus t. When we look at this proof, I'm going to give you a reminder of how to prove convergence. And the strategy is we would look at Sn minus s, taking this directly from the definition of convergence, less than epsilon. And then we solve for n in terms of epsilon and use this value for capital N. If we don't get a natural number, use the Archimedean principle to get n. Plug your n into the proof template below and work backwards till you get Sn minus epsilon. This is the subject of the last video I did. So for our proof, for limit of Sn plus Tn is equal to s plus t, we're going to start with the series minus the limit less than epsilon. So the series here is Sn plus Tn, and our limit, our proposed limit, is s plus t. So we subtract that and set it less than epsilon. Next, I'm going to solve for n in terms of epsilon. So I have Sn plus Tn minus s minus t is less than epsilon. So I can move my s terms together and my t terms together because I want to be able to look at them separately. And in fact, I can also isolate them in terms of, or make this, using the triangle inequality, I can say that the absolute value of Sn minus s plus the absolute value of Tn minus t is less than epsilon. Again, I'm using the triangle inequality, which is written right here for your reference. And now I can look at each of these separately. So since s is the limit of Sn, I'm given that somewhere in here, limit of Sn is equal to s. That means I can set this for some n less than epsilon over 2, for n greater than, let's say, n1, capital N1. And then I can do the same over here for Tn minus t. Because there's the limit, eventually there's going to be some n2 that I can have everything here within epsilon over 2. And now I can take the maximum of my n1 and n2 and set that equal to n. And then working backwards, I have my Sn minus s plus Tn minus t is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So now I'm ready to plug everything into a proof template. So given any epsilon greater than 0, I can choose n in my natural numbers such that n is equal to the max of n1 and n2, where n1 satisfies this condition here, because s is a limit of Sn, and n2 satisfies the condition over here for which we are guaranteed an n2 because t is a limit of Tn. Then n1, and again, n1 and n2 can be found since s is equal to the limit of Sn and t is equal to the limit of Tn. Then for any n greater than n, and again, n is the maximum, we have epsilon equals epsilon plus 2, and then working backwards, which is greater than Sn minus s plus Tn minus t. And you can see I go through the entire thing backwards until I get this right here, which is what qualifies this as the limit of this part here is equal to s plus t from the definition of convergence. The second theorem we have, or the second part of this theorem, is if we multiply Sn st, that the limit is going to be st. So again, if we kind of term by term take the new series Sn times st. So again, I start from the Sn minus s is less than epsilon. And like the previous example, we want to separate out the s's from the t's. And then we're going to use the triangle inequality to do this, but this isn't apparently immediately apparent. But we're going to introduce introduce the new term SNT. So, and our goal, again, is to get this form where we have our S's and our T's separate. So I have SNTN, and I'm going to have introduce my new term, SNT minus SNT. So this is what makes it okay, because they cancel out. And then I have my minus ST. Now I'm going to group these together. So my SNTN, I'm going to group with my minus SNTN. And then this, my SNT, I'm going to group with my minus ST. And now I can separate these out by the triangle inequality. And then from here, I can factor out my SN, and I can also factor out my T factor here. And this is what I get. And I'm back to a similar place where I was at the previous theorem. So since T is the limit of Sn, I can set this part to be arbitrarily small. Similarly here, I can set this absolute value to be arbitrarily small. In other words, I can choose it to be less than an epsilon, where epsilon is very small. And we also know since Sn and Tn are convergent, they are both bounded. So if m is equal to the max of these two terms here, the Sn and the T, and I'm going to set that equal to the max of m1 here and T, then SNTN plus T Sn minus S is less than m times Tn minus T plus m Sn minus S. So now what I can do is set my Tn minus T to be less than e over 2m. And I'm going to let n2 such that n greater than n2, capital N2, Sn minus S here is going to be less than epsilon over 2 divided by m. And then I can plug it into my proof, which I'll let you take a look at. And the last part of the theorem is the limit of Sn divided by Tn is equal to St, provided Tn does not equal to 0. And for this proof, I'm going to use part 2. So if I can show that 1 over t, this part here, if the limit is equal to 1 over t, then I can use this as one series times another series and use part 2. So I'll let you look at this. This is pretty much the same sort of thing we've been doing in proving convergence. This last part of this theorem, which I will give you without proof, is the limit of some constant k times Sn is equal to k times the limit of Sn. And also the limit of constant k plus Sn is equal to k plus the limit of Sn. And we're going to use this theorem here to prove that the limit of 4n squared minus 3 divided by 5n squared minus 2 is equal to 4/5. And you might recall we did this the painful way of using this definition of convergence and the strategies to do the proof. But here we're going to do this an easier way by using this theorem. And it's so tempting to say let's use L'Hopital or something from first year calculus, but again, we're doing proofs and things, and we're not using L'Hopital. Later, we'll prove L'Hopital later in this course. But one of the tricks we're going to do is we're going to divide anything by n squared because we know the limits here, n of 2 over n. It gets really small, so we know eventually it's going to get to 4/5. But let's go ahead and divide the top by n squared and the bottom by n squared. So we know the limit of 1 over n squared is equal to the 0, so the limit of minus 3 times 1 over n squared, using this here, minus 3 is the constant k, my Sn, so I can pull out my constant times my limit of 1 over n squared. The limit of 1 over n squared is 0, so then this whole line here, the limit of minus 3 over n squared is equal to 0. And now when I add the 4 to that using part 1, the limit of 4 is 4, and this over here is 0, so I get a final answer of 4. Similarly, the limit of 1 over n is equal to 0, so when I take the limit of this whole polynomial quotient, I have limit of 4 minus 3 times limit of 1 over n squared, and on the bottom I have limit of 5 minus 2 times limit of 1 over n. These two limits are 0, so I get limit of 4 over limit of 5, which is equal to 4/5. This actually really does look like first year calculus. Our next theorem, if we have two series with the limit of Sn equal to S and the limit of Tn is equal to T, If Sn is less than Tn for all natural numbers, then S is going to be less than T. And I do have a proof here, but in the interest of time, I'm going to skip this proof, but say that this is a theorem that you should know. A corollary, if Tn converges to T, and Tn is greater than or equal to 0 for all natural numbers, then the limit is going to be greater than or equal to 0 as well. And I'll show you how we can use this. So suppose the limit of Tn is equal to T, and Tn is greater than or equal to 0 for all natural numbers, right? Then we want to show the limit of Tn raised to the 1/2 is equal to T to the 1/2. A quick note, since we have Tn is greater than or equal to 0 for all n, we know that T is greater than or equal to 0 and square root of T is defined. And now I'm going to look at my definition of convergence, and I'm going to look at what it is that I need to satisfy, what condition. And that's that the sequence minus the limit is less than epsilon. So here my sequence is square root of Tn. My limit is square root of T. So the absolute value of my sequence minus my limit is less than epsilon. And here I'm working with the left-hand side of the equation, and I get it to this form through algebra, and you can take a quick look at that. And looking at this, what I want to do is use this theorem from the last previous video, and that is I want my Sn minus S, that's over here, which is equal to all of this. I want that to be less than k times some other sequence whose limit is equal to 0. So I have some other sequence here. I want to make this look like a k. That is a constant. And what I can notice is that 1 over square root of t is always going to be larger than 1 over square root of t plus something else, right? So if I add something to the denominator, it's going to be smaller than if I don't add something to the denominator. So I have this less than or equal to, which is what I was after to get to this form. So backing up a little bit, so I started out with my Sn minus S. So that's my square root of Tn, and my limit was square root of T. And I wanted to set that less than or equal to, and using all these calculations, I have 1 over T, absolute value of Tn minus T. Now, taking a look at Tn minus T, since the limit of Tn equals T, that means the limit of Tn minus T is equal to 0. So we have exactly this form. We have our Sn minus S is less than or equal to some constant k times some sequence whose limit is equal to 0. So what that tells us is the limit of our sequence Tn is equal to S, which is the square root of T. So that's exactly what we wanted to show. Our next theorem, suppose Sn is a sequence of positive terms, and the sequence of the ratios Sn plus 1 over Sn converges to L. If L is less than 1, in other words, the terms are getting closer and closer, then the limit of Sn is equal to 0. I'm going to use this theorem for our next example. Suppose x is between 0 and 1. Apply the theorem above to the sequence given by Sn is equal to n x to the nth power. I'm going to look at the ratio Sn plus 1 over Sn. So here I have n plus 1 over Sn. Some algebraic manipulations will get you x times 1 plus 1 over n. I want to see how this ratio converges, so I'm going to look at the limit of x times 1 plus 1 over n, and I do have this theorem over here to use. I can multiply through by my x, and then using this part of my theorem where I have the sum of two sequences, so I can separate this out to the limit of x plus limit of x over n. X is just a real number between 0 and 1, so the limit of x is equal to x, and the limit of x over n, as n gets large, converges to 0, so that's just equal to x. And since we were given that x is between 0 and 1, that means the limit of Sn plus 1 over Sn is less than 1, right, since it's equal to x and x is less than 1. Now by the theorem, since the limit is less than 1, that means the limit of Sn, which Sn is equal to n times xn, is equal to 0. and I'm done with this exercise. Next, we will have the definition of infinite limits. So if a sequence Sn is said to diverge to positive infinity, then we write Sn is equal to positive infinity, provided that for every real number m, there exists a natural number capital N such that n greater than capital M implies that Sn is greater than m. So in other words, no matter how large we want to choose our m, our number m, there's something in the sequence that's greater than m. So it's really unbounded above. Similarly, Sn is said to diverge to negative infinity, and we write Sn is equal to negative infinity, provided that for every real number m, there exists a natural number n such that any n greater than or equal to capital N implies that Sn is less than m. And similar idea, so any real number, no matter how small it is, we can always find something in the sequence that's even smaller, so it's not bounded below. So note that positive infinity and negative infinity do not represent real numbers, but they are notation we use to describe the behavior of certain sequences. Our first example is to show the limit of n squared is equal to positive infinity. In other words, no matter how large of an m we choose, we can always find something in the sequence, some Sn, that is greater than m. So we're going to substitute n squared for Sn, since that's how Sn is defined. So n squared is greater than m. And we want to show this is true for some n, little n, some natural number. And so our proof is, given m, a big M, we're going to let our capital N equal to m plus 1. Then any natural number greater than capital N is equal to m plus 1, and then n squared is going to be equal to m plus 1 squared, which is greater than m. And therefore, we have shown that we've shown the conditions we needed to show that Sn, the limit of Sn, is equal to positive infinity. And then we have this theorem: if Sn and Tn are sequences, all Sn's are less than Tn, then if the limit of Sn is equal to positive infinity, since Tn is larger, then its limit is also positive infinity. If the limit of Tn is negative infinity, since Sn is smaller, its limit must also be negative infinity. Here I have another theorem: let Sn be a sequence of positive numbers, then the limit of Sn is equal to positive infinity if and only if the limit of 1 over Sn is equal to 0. I'm not going to go over the proof, but I do have it here for your reference. That covers our main topic. So next I have a few problems for you to try. Here are 4 problems for you to try, so you can pause the video, give them a try, and on the next slide I'll have solutions. Here are solutions for the first 2 problems and solutions for the last 2 problems. That is it for this video. Thank you for watching.